Thank you for being part of Lecture 17 by Dr. Emanuel, Limits of Integration. Now, we have talked at our last meeting at limits of integration for second derivatives and for third derivatives. Now we're going to go into more detail. As we look at this graph over here, we can see that there's only one equation here that we're given. But we're given three different points. So we're going to need to find some more equations. Remember, the most difficult part of most problems is finding the limits. So let's find an equation for the 2 points on the xy axis where z is 0. We can use our y-intercept form, but we need 2 points to find out the y-intercept. So the first thing we need to do is find the slope, the change in y over the change in x, which gives us a minus 1/2. Where does it cross the b-intercept? Where does it cross the b line? The y, which gives us b, which is 2. Then we have the equation from y-intercept, y equals 2 minus 1/2 x. Now we want to look at the boundary points. They're all at 0, 0, x equals 0, z equals 0. So we're going to have x equals 0. And z2 is going to equal this equation here, 4 minus 4x minus 2y. y2 we already said is equal to what? 0. So when z equals 0 in this equation, what does y equal? So we see that y, we bring y to the other side of the equation, and we divide by 2, we get 2 here, and we get 1/2, or minus 1/2. So now, what about x? Well, we see x is 0, and when z equals 0, we have, when we have z equals 0, matter of fact, basically, we can look right here and see that it's 4. That's the maximum value for x. So you can look geographically, or you can plug back into your original equation. And that's what we have to keep in mind. Now notice we would like to do dz first, then dy, then dx. So to do that, we first found out the boundaries for what? Z, which is our internal. The boundaries for y, which is our second set, and now the boundaries for dx. Now, we mentioned that you can see graphically it's 4, but also if you solve for this equation, you will see that this equals 0, and for y equals 0 and z equals 0, y equals 0 and z equals 0, what you have is you bring this minus 1/2 of x to the other side, and you just multiply by 2, and you get x equals 4. So looking at this equation, we want to continue with our boundaries. We found all of the boundary points. Now we want to plug them into this equation. Remember, dz, then we're doing dy, and then we're doing dx. So our equation will be of this form. If we look at dz first, we have 4 minus x minus 2y. If you're looking at our dy, goes from 0 to 2 minus 1/2 x. And if we look at x, it goes from 0 to 4. And if we solve this equation, we will get, right here when we do our dz, we just get z, and then the lower limit goes to 0, so all we have is our upper limit. which is 4 minus x minus 2y. Now we're going to take the derivative, we're going to integrate in reference to dy. To do that, we get 4y, and we get just a y here because x is remain as a constant, a minus xy. And we take this squared and we multiply by 1/2 and we get minus y squared. And we're going from the limits from 0 to 2 minus 1/2 x. Okay, so when we plug in 2 minus 1/2 x, we multiply times 4. 4 times 2 is 8. Okay, and this is going to be our y. Okay, then we multiply 4 times 1/2 minus 1/2 x. Half of 4 is 2. Then we subtract. We're just plugging in an x here. We have an x times y. So that'll give us a 2x. And this will give us a 1/2 of x squared. Because we have an x. And then we have another x here. So that's minus 1/2. This minus out front times this minus turns this into a plus. Then we're just going to multiply 2 minus 1/2 x, that quantity squared. So let's transfer this all the way over to the top of the page here. This is what we had. So we keep this as 8. We see here that there's 2x and minus 2x minus 2x minus 4x. We see here we keep this as a minus 1/2 x. Now we multiply this out and we get 4 minus 2x plus 1/4 x squared. Now we want to combine terms. We multiply this times minus, just so we can keep our minus sign. This will be a minus 4. This will be a plus 2x, and this would be a minus 1/4 yx. Now combining these terms, we have 8 minus 4, which gives us 4. We have a minus 4 plus 2x, minus 4x plus 2x gives us a minus 2x. We have a minus 1/4 x squared subtracted from a 1/2 of x squared, and we get a positive 1/4 x squared. And so the next thing we would like to look at is we integrate this, and this 4 turns into 4x. This 2x, you multiply by 1/2, the 2 cancel, and you get the x squared. You have your x to the second is going to go to x to the third divided by 1/3. 1/3 times 1/4 equals 1/12. Now we're going to plug it in at our boundaries from 0 to 4. So if we plug in 4 for our x, 4 times 4 is 16. 4 squared is 16. So this minus and the plus 16, that goes to 0. Then we have 4 cubed, which is 64 over 1/12. So we have 64 over 12, which is equal to 16 over 3. So our volume is equal to 16 over 3. Now let's see if we can change the order of integration. Will that change? Let's change the order of integration just so that you can see how we can perform this. Before we did dz first, now we're going to do dx to be integrated first. So let's find out these boundary points again. So if we're going to do x first, we need to do, so we know x starts at 0. And now we're going to have to set this equation here equal to x. So then that gives us 4 minus 2y minus z. Then z, we know, starts off at 0. And we're given the equation. Z equals 4 minus 2x. Then we have when x equals 0, then what happens to z2? Okay. we set this equal to 0, we get 4 minus 2y. Okay, so we now have our x boundaries, we have our z boundaries. Now we need to just find our what? Y boundaries. So we know y equals 0. Okay, this is our equation. Now what about when x equals 0 and z equals 0? Okay, what are we going to do? We plug that into this equation here, and we get y2 equals what? 2. Okay, so this will be the new boundaries and how we would write it up. As we see, y, we start at the top with x. We start from 0, so 4 minus 2y minus z from x equals 0. Then we go to z, dz, and we're going from 0 to 4 minus 2y minus x. And then our last one is our dy. Our dy goes from 0 to 2. Okay, so they're seeing how these limits of integration are being performed. Now let's look at our last change as we relate to changing, first starting off with dy. dy, then dx, then dz. And I think we would have done everything. Okay, so at this point, we see that we're going to start off with dy, and we know it starts off at 0, and y2 is equal to this equation. Okay, so if we divide, we take the minus 2y to the other side of the equation. What do we get? We'll divide everything by 2. So 4 divided by 2 is what? 2. 1/2 z, the z's on that side, and a 1/2 x. So next we'd like to look at our x1. That's our next, that we know is 0. And now we have our x2 is equal to what? Okay, we solve for this equation. Bring x to the other side, and what happens? We get 4. We got to bring the z back to the other side, a minus z, and we already have a minus 2y. So when y equals 0, then x2 equals what? We plug in what? 0 here. We get 4 minus z. Now we need our z component. Z equals 0. And we already given this equation from the beginning. 4 minus x minus 2y. So when y equals 0 and x equals 0, what do we get? Y equals 0, x equals 0, so it equals 4. Z2 equals 4. So our equation of integration, we're doing for y first. It goes from 0 to what? 2 minus 1/2 z minus 1/2 x. Then we're doing for dx, goes from 0 to 4 minus 2y minus z. And then our dz goes from what? From 0 to 4. So now I think we have done enough for you. So I would like for you to do some practice problems. You'll be given a number of practice problems to do. Find an integral of the volume of a solid that lies below the surface of z minus z equals 1 plus x squared plus y squared, and above the region in the xy plane, bounded by y equals x and y equals 2 minus x squared. You do not need to evaluate the integral. We're just trying to get you to come up with limits. Find the integral describing the volume of a solid that lies under the surface of z equals xy and above the triangle in the xy plane with vertices 1, 2, 1, 4, and 5, 2. Okay, practice problem number 3. Find the integral for the volume of the solid that lies below the surface of z equals x squared and above the region in the xy plane, bounded by x equals x squared and y equals 1. Find the integral describing the volume, bounded by the surface, y equals 4 minus x squared minus z squared, and z equals y. Find the integral describing the volume enclosed by the unit sphere, x squared plus y squared plus z squared equals 1. Calculate the volume, illustrated below, lying in the first octave and bounded by the plane x plus y minus equals 0 and z equals 1. Okay, your final practice problem will be find the integral describing the volume enclosed by the cone z squared equals y squared plus z squared plus x squared plus y squared, and the plane z equals the square root of 3 over 2x plus 1/2. Hint, the equation of an ellipse is similar. X squared over a squared plus y squared over b squared equals what? 1. Well, enjoy your practice problems, and we will see you later. Thank you for being part of our study today.